Hello everyone, this is lecture 2 from course PE 645. In today's lecture, we will understand how to manipulate the image and the corresponding mask and extract the first order features from them. As mentioned earlier in the first lecture, to build a system, we need some images from a patient or multiple patients and the corresponding manually segmented images or masks, and then we need to mask or combine both of them together to extract the ROIs. For example, in this figure is a liver, it can also be kidney or lung, and then based on that ROI we need to extract the first order features, second order features, or any features that we need. Then based on these features we can apply them to a classifier to say that this image reflects a benign or tumor or reflect the grade of the tumor. It can also diagnose it can be benign or malignant based on that model. So let's begin. As you see here in the left figure, we have a liver scan for a patient and the corresponding mask, which is manually segmented by a doctor or clinician, and then we need to read both of them together and then extract the liver from that scan. We are going to apply the different scripts using Python. So as you see here, we have two different images. One reflects the sample liver image and the other for the segmented or manually segmented liver. So initially we need to import the packages we are going to use. We are going to use OpenCV package and Matplotlib for visualization. OpenCV will be used to read and write images, perform different operations on the images such as masking. The next step, we will read the different two images. So we will define here the path of the image and the corresponding mask. Then we will use the function mread from the OpenCV package to load the image by passing the path of the image and the criteria or the type of that image. It can be RGB or gray. So both of them, the liver and the manually segmented part, are in grayscale. So we will define the criteria to be grayscale. So in these two variables, case image and case segmented, we will have the two images. We can print the size or the shape of these images by using the property.shape. So if we executed the part, it will display the image and the segmentation shapes as 512 multiplied by 512. The next step, we need to apply masking between the image and the segmented part to extract the ROI. This can be done using the bitwise AND between the image and the corresponding mask. The reason of using bitwise AND here is that for the segmentation, as you saw in the figure, there was some regions with white and some regions with black. So if anything multiplied by 0 will be 0, and if anything multiplied by 1 will be similar. So the usage of bitwise AND here is based on hide all regions with black mask and keep the different regions with white mask. So before we crop the ROI, we can display the figures using Matplotlib to understand the meaning of getting the ROI. So we have the image, we have the segmentation image or manually segmented image, and by multiplying both of them, the white region will be multiplied with the liver and be kept like that, and the black region will be multiplied with the other parts and will be removed. After doing that, we need to remove all of the black region so we can only get the ROI for further processing, such as extracting the first order features or second order features. So how to do that? We can simply using the function bounding rect. This function will get the rectangle that capture a specific part in the image, ignoring the black pixels. So we are passing here the ROI and we will get X, Y, width and height. And by applying slicing, we can get the cropped image as we see here in this figure. So that ROI or cropped ROI will be used later for extracting the features. How to draw that figure? Simply, we create a figure. We have 4 subplots and we made a grid 2 by 2. So we define here the rows and the columns, and for each one or for each part of the grid, we define which image to display. For example, for the first part of the grid, we define 1 and we display the original image. and for the second we display the segmentation, for the third we display the ROI, and for the fourth we display the cropped image. We are giving a title for each of them: image, segmentation, ROI, and the cropped ROI. We are removing the axes, and if we didn't use to turn off the axis, the figure will be like that. As you see here, it will give X and Y axes. So the cropped ROI will be about 300 multiplied by about 200. What about reading a volume? When you get a case or a CT scan case, you will get it like a volume because the scanner will produce the volume as slices, where each slice reflects an image. So if you have a volume of images for a corresponding or for a patient and the corresponding segmented parts, how to handle that? There are different formats that you can get the data from a hospital or a public resource. It can be in DICOM file or NII file. In that example, we will read from an NII volume. So as you see here, we have two volumes, one for the liver scans and the other for the segmentation, and the extension for each of them is .NII. So how to handle both of them and extract the different slices from these volumes, so you can apply later masking between each slice and the corresponding mask and extract the features from each slice. There is a package called NIBabel that can read and load the files from NIIs. So we define the passes for the volume and the segmentation and use the function load from NIBabel package by passing the NII file, and we get the object for each of them. Then to get the data from the NII files, we use the function getIfData. So if we only executed the upper part of the code to get the shape of the volume and segmentation, you will find here each image is 512 multiplied by 512, and we have 75 slices in that volume, and also for the segmentation we have corresponding 75 segmentations. The next step, we need to extract these 75 slices, and 75 here is not a fixed number. It can differ from a case to a case. You can find 80, 90 or 100. It depends on the configurations applied to the scanner for that patient. So to do that, we have defined two storage folders for each of them. One is called volume slices and the other is segmentation slices. And here we create these folders if they don't exist by checking. If they don't exist, we create them, one for the volume and one for the segmentation. Then we apply a loop, and in that loop we extract each slice and then we store it in that folder. So how to do that? Simply, as you see here, we have three values and the index in Python starts with 0. So we need to get the number. So by knowing the shape, we can access that number by getting index 2. So we made a range, or we made a loop from 0 to 75, and each iteration here access a single slice by getting the whole image with a specific index. I starts from 0, 1, 2 and ends with 74, because the last index will be that number -1 in Python. So let's simply, before understanding the benefit of these lines, let's just get a slice and store it using the mwrite from the CV package, and let's execute the code. These two folders, one for the volume and one for the segmentation. If you open the volume, you will find the images or the scans are rotated, for example here. So we need to rotate it so we can visually understand or see it better. This is the first issue. Second, if you open the segmentation slices, you will see that most or all of them are in black. You don't see any segmentations here. This is the second issue. So to handle the first issue, you can use rotate 90 degree from the NB package or NumPy package. So if you executed the script again, you will see that the volumes are rotated and you can visually understand the scan. And for the second issue, this issue depends on the data itself and the type of segmentation. If you simply printed the unique value of the slice you will see that the unique values for the slices in the beginning are zeros, and then it starts to be 0, 1, and then 0, 1, 2, and so on. If you found that, this means some images have only one class or one segmentation, and 0 here means background, which is black, and some of them have 1, which means this defines a specific class, and 2 here defines a second class. How do we handle that visually? You simply reflect each number of them to a grayscale value. The maximum grayscale value is 255, so we can simply split the scale into 3 values. Why only 3? Because the maximum number of classes here we are getting are just 3. So if you found in a case 0, 1, 2, and 3, you split the grayscale into 4 values. So we simply here made a slice for all values with 1, a change 1 with 127, and a change 2 with 255. If we applied that, you will see the segmentation slices are updated, and you notice that the slices in the beginning doesn't have a lever, so there is no segmentation here, and the lever starts to increase. So let's simply open that slice. So as you see here, the lever with a grayscale value of 127. What about 255? As you see in that image, there is a lever with 127 grayscale value, and you see here 2 regions in white that reflect the values 255, and simply this can be described during the data acquisition. You can retrieve a data that says we are segmenting the lever, and we are then segmenting the tumor in that lever. So the white regions here reflect the tumor. So if you don't care currently to distinguish between the liver and tumor, you can simply change both of them to 255 and execute the script. You will find all of the images are in white. If you opened any of them, you will find the liver with the 2 regions will be in white. So after extracting the slices from the volume, we can then mask each slice in the volume and the corresponding mask and start to extract the features. In this lecture, as mentioned, we will deal with the first order features. First order features here refer to statistical measures which are derived directly from the pixel intensity within a specific region of interest. These features gives different insights on the image texture and intensity distribution without considering any spatial relationships between the different pixels. There are many common first order features such as mean, variance or standard deviation, skewness, kurtosis, and entropy. This table here defines the different first order features with the different formulas and the significance of each of them. For example, the mean here performs a summation on the whole image, and as we are dealing with a 2D matrix, there are 2 summations, and then taking the average by multiplying m by n, which means the number of columns by the number of rows. Another example, the skewness here, which indicates the degree of symmetry of the gray values corresponding to the center of the distribution, takes each value and subtract it by the mean value to the power of 3 and divides that summation by the standard deviation power to 3 and then divides by m multiplied by n, and so on. These 2 figures distinguish between the skewness and kurtosis. Kurtosis measures the degree of tildness. Simply, it shows how much of the data is in the tails compared to the center. Skewness is a measure of the probability distribution asymmetry, which indicates whether observations or the dataset are concentrated on one side to the other. So, the distribution can be right skewed, as you see here, which is called positively skewed, or left skewed, which is called negatively skewed, or symmetrical, which is called zero skewed. And for the kurtosis, the distribution can be mesokurtic if the kurtosis is 0, which is considered normal, and if the value is greater than 0, the distribution will be leptokurtic, as you see here, and if the kurtosis is less than 0 or negative, the distribution will be platykurtic, as you see here. So based on the value of the feature that is extracted from the region of interest or ROI, you can say that a slice is positively skewed and platycortic, or positively skewed and leptocortic, and so on. So how to extract these features? Let's consider this example. This is a 2D image or 2D matrix that we need to extract the different features from it. You can use these formulas directly without any pre-processing, but the limitation or the disadvantage of these formulas is during dealing with large size image such as 2K by 2K, because when you code these two summations, you will use two inner loops. So the time of execution of a simple slice or a single slice will increase by increasing the size of the image. There is a quick approach by using the histogram. First, you need to build the histogram for that matrix or image. To build the histogram, you need to define the bins of that histogram, and in that case, we have just here 5 values, 1 to 5, so we have in the x-axis 5 values, and for the y-axis, you put the frequency or the occurrence of each bin or number. So for example, the value 1 here is repeated 6 times, and the value of 2 is repeated 8 times, and so on. Based on that 2D histogram, we can calculate the different first order features. How can we do that? You start by getting the count, and count here, you are counting the y-axis. So you count 6 plus 8 plus 3 plus 5 plus 3. So we have the value of 25. And the summation will be the sum of the sizes of each bin of them. Mathematically, you are summing 1 plus 2 plus 4 and so on until you reach 5, but this will take longer if you are dealing with large image as mentioned. But using histogram, you are just multiplying 1 multiplied by 6, which is the size, 2 multiplied by 8, 3 multiplied by 3, 4 multiplied by 5, 5 multiplied by 3, and then you sum of all of them, and then you get 66. You have the count, you have the sum, you can get the mean by dividing both of them together. 66 divided by 25, which is 2.64. The variance, to calculate the variance, you are subtracting the mean value of each pixel. So here, we are subtracting from each bin, as you see here, the mean value. You subtract 1 minus 2.64, and so for 2, 3, 4, and 5. Each part of them is power to 2 multiplied by the frequency and divided by the count. So simply it's similar to the mean, but you subtract each bin from the mean power to 2, and the value will be 1.8. The standard deviation is the square root of the variance, so the standard deviation will be 1.35. The skewness, the numerator will be similar to the variance, but power to 3 instead of 2, and you multiply 25 by the standard deviation power to 3, so the value will be 0.38. For the kurtosis, similar to the skewness in calculation, but instead of the power of 3, you change it to power of 4, so the value will be 1.85. There is something called excess kurtosis, which you subtract 3 from the kurtosis value, and the negative 3 component here is added to the kurtosis to make it centered around the normal distribution, and in that case we call it excess kurtosis, and that value will be negative 1.14. Based on the results, we can say there is a weak positive skewness because the skewness is positive and it's very small, so it's weak positive. This indicates that the data is approximately symmetric with a slight skew to the right. Also, based on the excess kurtosis, we can say it's platycortic because it's a high negative kurtosis, and this indicates that it's very flat and a relatively low number of outliers. So let's move to code the different equations and get the results. Here we are creating a NumPy array with the matrix, which we are going to change it later to the image of the liver. But here we are just introducing an example to understand how to calculate it mathematically and programmatically. So we need to calculate the histogram, we need to get the minimum and the maximum values, and for each bin of them, we are counting the non-zeros parts and appending it to the list. So if we simply printed it, we will get the same count as we calculated it mathematically, 68353. And the count here, we are summing the histogram, so we are using the sum function. Then we determine the range, which is a range from the minimum to the maximum values, which will be 1 to 5. And to calculate the sum, we multiplied each value here by its corresponding value in the range to get the size. And by summing that, we get the sum. And to get the mean, we are dividing the sum by the count. And to get the variance, we are subtracting each bin by the mean powered to 2, as we saw in the example. And then we multiplied this vector by the corresponding size. And then we get the sum divided by the count to get the variance. And to calculate the standard deviation, we are squaring root the variance. Similar to the variance, we are calculating skewness and kurtosis, but instead of using power of 2, we are using 3 and 4 respectively. And instead of using count, we multiplied the standard deviation bar to 3 and 4 respectively. And for the excess kurtosis, we subtracted the kurtosis from 3. And then we printed the different numbers and plotted the bar chart of the histogram. If we executed that code, you will see we are getting the same bar chart, and also we are getting the same results. For example, the variance here is 1.83 and the excess kurtosis is negative 1.14. So how can we do that with the image? We earlier were capable of multiplying both of them together to get the ROI of the liver, and then we understood the first order features and how to calculate it on a matrix. So instead of using that matrix, we are just simply replacing that matrix with the image. So as you see here, we read the two images for the image and the segmentation, and then we applied the ROI, and then we got the cropped part. And this snippet is similar to the first code we discussed, and then we calculated the histogram using the same operation. So here we just removed the matrix we calculated from that example to put the snippet to load and crop the image of the liver. We added the part here that we are going to discuss, but simply let's remove it to understand the difference. The rest of the code is similar to what we discussed. If we executed the snippet, you can see here the x-axis is from 0 to 2055, and you will see that the frequency or the size of the pixel at 0 is more than 25k, and this reflects the background, which we need to ignore it because the background shouldn't be included in the features. How to do that simply? We know that the background is at pixel 0, which is in black, so we can simply slice the histogram and remove the pixel at 0, which reflects the black or the background. So instead of getting 0 to the maximum, which is 214, we will get from 1 to 215 by that slicing. And we also need to increase the minimum, so instead of getting the minimum at 0, it will be the minimum value will be 1. If we kept that part and executed the code again, the background will be removed and the view will be from 1 to 214 or 255, and it depends on the liver intensities or the case you are dealing with. So this will be the output with the different features, and you see here the skewness is negative, which means it's left skewed or negatively skewed. So if you simply draw a line here, you can understand that it's left skewed or negatively skewed from the center. And for the excess kurtosis, it's a positive value, which reflects that case or slice is leptokurtic, But if you didn't ignore the background, as we saw, it will be included in calculating the features, and this can be it change the output dramatically. For example here, the excess kurtosis, it changed from 2.6 by ignoring the background to negative 1.79 by including the background. So this means this case, or the kurtosis, or the excess kurtosis for that case or slice, it changes from being elliptokurtic to platykurtic. So you need to consider that issue when dealing with ROIs. Then we need to apply that to a volume. A volume reflects a patient, and a patient reflects a record in the database or the features or the table you are going to put or pass to the classifier. But we have different slices. Each slice has a corresponding segmentation, so you will get 75 records. One approach to deal with that, we have 75 slices in that volume, which means we can get 75 records in the database, but to overcome that, we can get the average of the different features in that volume. So we loop on each slice, calculate the features, and then take the average of all of these 75 slices, which will reflect the average behavior of the patient or that case. How to do that? We simply built a function called first order features that accepts the image and mask, and we took from the previous code the part that begins from extracting the ROI until the calculation of the excess kurtosis and encapsulated it in a function that can later combines the results into a list and returns it. So this encapsulated function is a way to organize our code. It accepts the image and the mask and then returns the results, which are the features. We have two volumes that we extracted from the second code from the NII volumes, and then we made a loop that loops on each slice, read each of them, and then calculate the results of the first order features and append it to a list that we created here. That list will later be used to calculate the mean. So we will have about 75 values. We will get the mean of the kurtosis, the mean of the skewness for all of these slices. And then we will print the average of that case. But you will notice here two things. The first, we are using the replace function. The second, we are skipping background only images. Why? If you noticed, during writing the images and extracting from the NII 3D volume to images, we wrote the volume with a prefix volume slice and the segmentation with a prefix of segmentation slice. And we need, during reading each image or each slice, we need the corresponding segmentation image of it. So we can simply get that name, for example, volume slice 66, and to get the corresponding segmentation slice, we can simply change the prefix from the word volume to segmentation, as we did here. So we used the volume name, the file, the image file name, and replaced the word volume with the word segmentation to get the corresponding segmentation file. And second, as you see here, for volume slice 4, 5, or 6, if you went to the segmentation slices, you will find from segmentation slice 0 to segmentation slice 45 for that patient, there are no liver. This means the scanner didn't capture the liver at that slice. So we cannot extract the ROI, which can raise an error during executing the code. So to avoid that, we simply took the segmentation file and made a summation. As we know, the background is 0, so if the background consists only on zeros, so the summation will be 0. So we made a condition here: if the summation of that segmentation is 0, continue, just skip that case and don't append the results. If we executed that code, you will find that the number of images that contained ROIs is 29 instead of 75, and it calculated the average values of each of them for the summation mean variance until reaching the excess kurtosis. So in that lecture, we dealt with reading images, masks, and getting ROIs, grouping and ignoring the background. We dealt with how to handle NII files and read the data from it and extract the different slices. Then we went through the first order features and dealt with a quick approach using the histogram to calculate each of them, such as kurtosis, standard deviation. We handled a numerical example and validated the results with Python programming. Then we applied that on a simple slice and its corresponding mask, and then we applied it on a 3D volume by taking the average of the different slices.